Shekhar sir, I'm audible to you.
Yeah,
Okay, sir.
can you hear
So,
me?
yes, sir. You are also audible. We will start the session at 11:30 exactly.
Yeah, okay.
Good morning, participants, and welcome back for the session 5 uh, of Sustainable Solutions in Hybrid Vehicle FTP, which is sponsored by AICTE and organized by Mangalore Institute of Technology and Engineering. So, this particular session is of the topic electrical machines and selection of motor and controller for EV and HEV by Mr. Shekhar Malani, MD, Devise Electronics Pune. So it's my privilege to introduce Mr. Malani to all the participants. Mr. Malani is presently a director of Devise Electronics Private Limited, having 20 years plus of diverse experience in automotive powertrain industry from service network to research and development. 10 years EV powertrain systems, integration projects, development, experience of multiple EV components, 20 years plus of embedded product developed across multiple domains, has experience in engine, vehicle, after treatment, and powertrain controls for multiple emission regulations, hybrids, and electrical vehicles. Mr. Malani has experience in design and development of aftermarket diagnostic tools of troubleshooting processes. Mr. Shekhar Malani has experience of working with multiple engine and vehicle OEMs, including Chrysler, Nissan, Freightliner, Tata Motors, Leyland, and across multiple geographies, leading a young company of 40 plus employees, director in multiple companies across the functional areas. Mr. Malani has specialties in electrical powertrain integration, electronics integration with engines and vehicle design and development of SCR, DOC, and DPF, after treatment system integration of engine and after treatment system application of hydrocarbon and urea dosing systems, development of OBD diagnostic for engine and after treatment systems, vehicle CAN networks, and vehicle interfaces, vehicle diagnostic test tools and interfaces, industrial standards of SAE, J1939, SAE J1587, and so on. And it's our department privilege to have you for the session, sir. The session is over to you, sir.
Thank you, Mr. Madhusudan, uh, for the detailing of my career, and thanks everyone to have me here for this lecture. Again, thanks to the Mangalore Institute of Technology and Engineering. I'll just share my screen, so please do let me know
Sure, sir.
once it is visible.
Yeah.
Is the presentation visible?
As of now, it is not, sir.
So it's asking for some permissions, Madhusudan.
Like what, sir? Permission regarding?
For for being able to present.
Yes, sir. Need to make the presenter correction.
Yes. So, is your presentation in the Google Slides or it is in the separate windows in Microsoft PowerPoint?
It's in PowerPoint.
Yeah. Then present. Just click on the present now and click on entire screen, sir.
Yeah, that's what I did. Uh,
Then
okay. Is it showing up
just
now?
click on the window. Now it is showing up, sir. Now it is showing up. So you can just
Okay.
yes, sir. Now it's
Okay.
done, sir.
Okay. Sorry about that. Good afternoon, everyone. We'll start with discussing about e-machines and most essentially the powerhouse of the electric vehicle, the motor, and the motor controller or the inverter. So, what is the motor? So, if we take like a view of, let's say, I would say, artistic view, if we consider that, and then if we look at what exactly is a motor, then we can say that the motor is an arrangement of copper coils, steel laminations, and the permanent magnet. So the permanent magnet is a optional element. It may not be there in every type of motor, but we'll surely see the copper coil and the steel laminations in every type of motor, right? So that's a simplistic view of what is there, but let us talk about more. Uh, why it is very significant to talk about the motor. And when it comes to electric vehicle, we expect some targets to be met at the vehicle level. And that target at the vehicle level has to come down to what the battery pack has to do, what the motor has to do, and what is expected from the powertrain and drivetrain. Now, typically, if we see that those flow down at a specification level at the vehicle target, enters the V model of development that the automotive uses. And from a full vehicle to get into the module level or the subsystem level with the mechanics, the hardware, the software, then go down to the component and algorithm level, and develop and start with the testing and the integration. So that is the flow that we typically talk about. And here, if we look at the high level expectations, the expectation of EV is actually not only to be as good as the IC engine vehicle, but we want, all of us want a better than the IC engine, better than IC engine vehicle, so that we move towards the electric vehicle. So different classes of the vehicle, we have different requirements. There may be different requirements in the acceleration. There will be requirements on the weight of the vehicle. There will be requirement on the grade at which it should launch or it should be able to start itself. And obviously the range, a very, very important element for the electric vehicle, which I think you have already had a significant discussion on. So what we want is a better than IC engine, and we want a good range, and we want good handling. And those are the things, if we come down to a component level and come to the electric drive. So electric drive being the summation of the motor plus the motor controller plus the drivetrain integration of the motor. Now, motor could exist or could be placed at different places in the drivetrain. It can take the place of the original transmission. It can be put somewhere in the middle, or be a mid drive. It can go on the drive axle. It can go on the wheel or mounted next to the wheel. So there are different places where the drivetrain integration can happen, and we also have to include that into our requirement for the electric drive. So there is a requirement to have a high torque. And when we talk about high torque, torque directly converts to the requirement of a high magnetic flux density. So my vehicle level requirement is high torque, and my component level requirement is that I want a machine that will be high magnetic flux density. Then I want high frequency and high efficiency. I want my overall losses to be low. And that means that the wire we use, or the winding we used, has to have a thinner gauge, and there has to be lower loss in the core, and lower loss in the rotor and the stator. So that is what the requirement is. And this can give us the patch of this high efficiency, which is required for the city driving. At the same time, we want highway driving to be there, and for that we want high speed and high strength. So high speed translates into high strength or high power, and for this we want to get into the high speed, get proper highway driving, and so these are the three sets of high level requirements that we have from the electric drive. So high power density. So when we say power density, it is power by the weight. How much we can package. High speed range. We have high efficiency requirement. We have better NVH requirement. Reasonable cost, very important for the Indian market. High reliability. More and more customers are looking at that. because warranty wise and serviceability wise, they want the motor to be good for life, that is 10 years of the vehicle. High intermittent load capability. So overloading at some time, some instances, wide constant power zone, and high torque density. So all of these are requirements that we can further drill down and also use for the selection of the motor that we want to use. So if we look at the complexity of the overall drive system, so this is looking at one of the most complex systems being used in the electric vehicle passenger car industry right now. So you see the three elements coming here. One is the motor itself. So this is the motor itself, motor housing, stator, and the rotor, right? And then we have the adaptations or the integrations, and we see the integrations on both sides. So here we see the gearbox and the parking lot lock and the end adaptation. So that is one of the element. And second is the mounting. So here we see the mounting elements after the bearing plate. And the element coming on top of it and integrated. This is not necessary to integrate it to the motor. But when we bring the power electronics or the motor controller or inverter very close to the motor itself, what we are essentially doing is reducing the losses. Though we are increasing the complexity of the installation, we are reducing the losses, and that is where the power electronics coming into the system, very close coupled to the motor, that is important. So a supplier would like to offer this complete subsystem to the vehicle manufacturer. Just like the engine and all its accessories, we have the motor and all the accessories and the mounting coming together. Now this here is a 125 kilowatt motor. Obviously, we'll see ranges as we go on. There is a lot of ways in which the motors can be classified. The most simplest way of classification is the AC versus DC, which is looking at what type of input electrical power it is using, whether it is AC or whether it is DC. And within that, within the AC, then we have a lot of separation. We have the synchronous motors, wherein we could have a synchronous brushless motor. We have a sinusoidal motor or a AC motor, which again is a brushless. And within that, we can have a permanent magnet motor, which can have surface permanent magnets or interior permanent magnets. We'll talk about those. And the wound field. So there is synchronous AC motor and sinusoidal motor, reluctance motor. And then we have the asynchronous motor or the induction motor, that again we'll talk a bit about. And we have variable reluctance motor, which is synchronous reluctance or switched reluctance motors are there. So we'll talk about some of these motors which are applicable to the electric vehicle applications. Now, when we talk about the EV motor comparison, there are some things that are more suitable for certain applications. So the most widely used motors, you can see them here, the brushless DC motor, the permanent magnet synchronous motor, induction motor, the synchronous reluctance motor, and the switched reluctance motor. So this is one variety, this is the second variety, and this is the third variety. So we can say that there are three varieties. Internally, these two are fairly different. this is fairly different, this is fairly different. Now, when we talked about where the magnet is, these two type of motors have the magnets. The induction motor does not have a magnet. It has coils or windings or bars on both sides. So both sides are still magnetic material. And on the switched reluctance motor or the synchronous reluctance motor, we do not have the magnet, and we have coil on only one of the or winding or only on one of the sides. So the second field is not winding. We are just playing around with the parameter called as reluctance. Now, some of you may be aware of this parameter. Reluctance is nothing but the resistance of a magnetic circuit, and by modulating or by effectively designing the difference of the reluctance, we can make it purposeful for the motor development. So that is what these two motors work on. Now, when we look at two and three wheeler applications, then the most preferred motor is the BLDC type of motor. There are two applications. One is the mid-drive installation, and second is the hub motor or the in-wheel application. And both of these preferred is still the BLDC. There are obviously some customers using a PMSM, permanent magnet synchronous machine. But hub motor, mid-drive motor, and typically we'll see a power range of 250 watt to 6 kilowatt. So normal two-wheeler will be like let's say 2 to 3 kilowatt, and a performance bike may be 4 to 6 kilowatt, right? And then there are low speed applications which you cannot take above 25 kilometers and so on, 25 kmph. Those will fall in the 250 watt and 500 watt kind of zones. Similarly, when we go up to the three-wheeler, again, the BLDC is preferred. And for light cargo applications, the induction motor may also be preferred. Not to mention the others can also be used. Again, here the most preferred is the mid-drive motor and a single motor. Instead of having motors on all the wheels, single motor ranging from 3 kilowatt to 10 kilowatt. When we go to passenger and commercial vehicle applications, then the most dominant is the permanent magnet synchronous machine. And within that, the IPM, interior permanent magnet, seems to be becoming the preference. For a small car, we'll have a 5 kilowatt to 15 kilowatt type of motor. And for a performance car, the range may be very wide. We may have a 30 kilowatt to a 400 kilowatt type of range. So if we look at Indian market, then what we have is the current offerings of Tata and Mahindra. They typically fall in this 15 kilowatt zone. And then when we talk about the MG EV and I think the Hyundai also, they'll fall in the 30 kilowatt range. We don't have a significant high performance, high power application in India right now. And then when we talk about buses and trucks, the most preferred is induction motor because of the cost. The permanent magnet motor, because of the magnet cost, becomes very, very challenging when we want to integrate it for a bus or a truck application. So these are the different types of market segments that we have. So if we look at a modern stator, now all of you must be familiar with this term stator. So this is the stationary part of the vehicle, of the motor. In most cases, it is the outer body of the motor, and it is going to uh, provide a place for putting the windings. So copper windings are taken and they are put onto the motor, and this is what you are seeing here is how there is grooves made all along the periphery, and within the grooves you have the windings going, right? So there is a stator body, uh, external body, which you see here. Then there is the laminated core. On the other side of the core, you will see the grooves, and the grooves are where the windings go. And in order to keep them in place, there is a cover slide that may be there, right? So this is the stator coming from Audi e-tron application. And then you can see the power electronics connection to the three phases. So overall, one more look, if we look at alternate design of the stator, we can see how the power electronics is coming in and getting to the winding, and the winding is distributed across. And so this is the portion of the stator. Then very, very minute gap. We are talking about some or less. So we are talking about gaps of 0.3 to 3 mm. So that is the range of the gaps between the stator and the rotor. And we have this very little gap. And on the rotor, then, depending on the type of the rotor, we will have the bars, or we will have another set of windings, or the magnets. Right, so if we just look at the stator, you can see how the stator looks, right? And this is kind of a design that can work with multiple types of motors, not just a particular type. So stator design by itself is also kind of independent to some of the uh, requirements of the final application. So within the stator, we have insulation sleeves. On the insulation sleeves, then which get embedded onto the stator core. The core is nothing but made up of thin steel plates. This is called as laminations, and multiple of them are stacked on top of one another. And this is purposefully done in order to create individual circuits of their own, so that any self-excitation currents or eddy currents that may generate, they short circuit on the plate itself. So they are not going to travel the top and bottom. And that is why these independent plates are made. So that keeps the overall losses of the magnetic field to a minimum. So when we talk about the steel, it is becoming very, very important, the choice of the steel. And there are different compositions or additions that may be done, different thickness, and then what is the flux density that it can generate when we are looking at zero point 0.8 kiloamperes per meter current loading, and 2.5 kiloamperes per meter current loading. Right, so we are seeing these different flux densities, and that is the prime importance. So if we want to go higher on the flux density, then we have to go to copper, cobalt ferrous, with 49% cobalt and 49% iron, 2% of vanadium in there. Uh, then we have nickel, ferrous. So all of these obviously have some cost implications as well. Now, how do we place the windings in the stator is also very, very important. And we can take two mechanisms in which we can do. One is we can have concentrated windings so that we have arrangement wherein our poles coming from the same winding are together, and we have concentrated windings that offer higher fill factor. So the amount of wires that can go into the slot is going to be high, and it is also going to be simple for manufacturing purposes because we can put one phase at a time, right? It will also be better for thermal and electrical isolation between the phases. So one phase at a time can be installed. When it comes to distributed winding, then we cannot do one phase at a time. We have to have a complex machinery wherein all the three phases are getting installed or getting assembled at the same time. Right? So there are some benefits of concentrated windings versus distributed windings. This is also looked as and called as bar wound, which is concentrated, versus stranded coil, which is distributed. So when we go for bar wound, as we said, we have higher slot fill factor. We have shorter end turns, so the overall DC resistance is less, packaging is better, construction of the slot is simpler, and there is a larger surface area in the end, which gives better heat dissipation. So the slot is like this. It is broader from the back side. That means the stator body is in more interaction, so heat dissipation area is more compared to the slot for the stranded coil. And overall bar wound or concentrated winding, they give better performance in transient conditions. The bad part about the bar wound is that the AC resistance or the stator copper losses are higher, and skin and proximity effects are also higher. So there is a lot of magnetic field which is getting into the skin effect or proximity effect because the winding is concentrated. So the field is very powerful. So here we again see a couple of brushless DC motors. So one is, as we said, a hub motor or a wheel installed motor, and the second is something which can be uh, put in the middle, and that is a different construction altogether. So you see the length versus the breadth or length versus the thickness characteristics is very different. This is the interiors of the hub motor, and you can see that once we take out, we can see the different components. Now, this is obviously a very low-end motor, which is not having all the intricacies inside. So brushless DC motor, when we talk about the advantages, it gives a high power output. It also gives high efficiency. The rotor losses are less. Different designs are possible. High speed performance is good. It allows heat to be easily removed. However, there are some disadvantages also. A DC motor has a higher ripple than a PMAC motor. And we'll talk about the PMAC motor here shortly and how the torque ripple comes. And this trapezoidal back EMF as well, we'll talk about that shortly because that is a characteristics of the DC motor. So there are some things which are not optimized uh, for the brushless DC motor. So if we have something which is very simple, then a simple application which is not going to see a lot of excursions, like let's say a fixed speed application, then what we can do is definitely we can use the brushless DC motor for the best efficiency point. However, that doesn't happen in the actual vehicle. So here there is a mid-drive motor from one of the tier one manufacturer, and we can see some of the elements. So there is a BLDC permanent magnet inner rotor motor. So the rotor is in the inside and the stator is on the outside. It is using Hall sensor. These sensors are required to know where the rotor is with respect to the stator so that the next winding can be appropriately energized. And then we have the specification. It's a 2.5 kilowatt motor, 72 volt DC. Peak power is 5 kilowatt. So typically we'll see peak power in the 1.7 to 3x the nominal power. And peak torque here is 39 Newton meter without a reduction ratio. So if we add a reduction ratio, we can further increase the torque. The peak torque is 16 Newton meter. No load RPM is 4000 RPM per minute. And peak efficiency is greater than 90%. Peak battery current is 90 amperes max. So max it needs 90 amperes and the weight is 9.5 kg. Now compared here, we see the hub motor assembly directly mounted on the wheel and 60 volt DC. Rated power is 0.8 kilowatt, so much lesser power. Peak power is only 1.2 kilowatt. Peak torque is 75 Newton meter. So here you see that since it doesn't have a gear, it is directly mounted on the motor, on the wheel, the peak torque is significantly higher than the mid-drive motor. And the max speed here it can give for the vehicle speed is 43 kmph. So in the case of a hub motor, the rotor speed directly interacts with the road speed, right? So here this is 8 kg without considering the wheel. So you can see that weight wise also it is expensive. So that is the different types of BLDC options for a two-wheeler type of application. Then when we talk about the PMSM and PMBLDC, so this is PMSM is nothing but PMAC. It's a permanent magnet motor, but driven by AC waveform, and PMBLDC is driven by the DC waveform. So that is primarily the only difference. But the arrangement of the flux and the air gap and the windings is slightly different because here the distribution of the flux is also different. So when we say PMSM, typically we'll be using a distributed arrangement of the windings, and the flux distribution is going to be sinusoidal. Here we are going to have in the PMBLDC, we are going to have a trapezoidal distribution of air gap flux, and we will be having concentrated winding arrangement of the stator. Here with the sinusoidal distribution, we have the benefit, or we can go to more optimized strategies like the field oriented control or direct torque control or vector oriented control with regards to controlling the torque of a PMSM. Whereas in a PMBLDC, it is very simple and it is coming directly with the speed control. It is going to be fairly dependent on the current with the flux. So here the option of optimization by means of software is limited in a PMBLDC. The bad thing about the PMAC is that for accurate feedback, it needs to have a expensive position sensor, which will require a absolute position encoder or a resolver, whereas on the BLDC, a low cost Hall position sensor can be adopted directly. Now here, the other thing is the back EMF. So when the motor is doing its motoring, it is also acting as a generator. Just that the motor EMF is much higher than the generator EMF, but there is this self-excitation and the back EMF that is coming, which is taking a sinusoidal waveform. And on the BLDC side, it is having a trapezoidal back EMF that is coming back. So the excitation and the back EMF, the waveforms match. So sinusoidal and sinusoidal, trapezoidal and trapezoidal. One more element that we have to look at in the motor construction is the alignment of the flux on the rotor. So is the flux getting produced radially? So it is coming along the sideways of the rotor, or it is getting produced axially, that is along the axis of the rotor. And there we have this different options where further optimization can be done. Today, if we see the EV world, 90% of the motors being used are radial flux motors. There is a lot of work happening on the axial flux. There are some customers who are now going with to launch with axial flux, but axial flux is still in its final stages of R&D. Now, what do we mean by the radial flux and the axial flux? And here we can see some of the options in which we are changing the flux path in the rotor by placing the magnets in a certain manner. So when we say that the stator is generating the magnetic field, the magnet in the rotor is actually acting as a flux barrier. It will not allow the stator's magnetic field to pass through it. So the stator's magnetic field is going to come like this, go like this, right? And then complete the path on the stator. So that is the kind of path it will follow. So by placing the magnets, we can define how the waveform should travel, or how the flux should travel rather, on the rotor surface. And this is again, we see one more alignment where we have flux barriers. We have placed the magnets in a distributed manner. So there is very little room for the magnetic flux to go. Now, looking at these two designs, you can understand that the torque of this design will be higher, because here the concentration of the flux lines, right? The flux uh, per unit area is going to be very, very high. So higher torque will be generated, right? So that is the type of difference here. Now here we see a longitudinal arrangement of the magnets, wherein we have completely changed the alignment of the magnetic field. So the quadrature field versus the direct axis, the complete opposite element is there with this design, because we have placed the magnet in a different manner. Here again, we can see another different type of placement of the magnet. So different varieties, a lot of IP is being generated right now with this different placement and optimization for the IPM. So when we talk about these magnets, there are different types of elements. There is ferrite, there is samarium cobalt, alnico, and the most widely used, the rare earth metal, is the neodymium ferrous boron. And if you see, this is the natural magnetic field strength that they produce. So what we want is that the magnetization should stay for a long time, whereas in ferrite, in order to demagnetize it, uh, a not so uh, powerful magnetic field can also demagnetize it, and that is where we want something which is more stronger, more reliable. And neodymium ferrous boron, that is the most widely used metal for the permanent magnet motor. Now, we'll not go into detail here, but these are just some of the specs or the differences in the basic characteristics of these different magnets. So what is happening? How is the world changing? So let us take an example of the Prius platform, Toyota Prius platform. Uh, when they launched in 2004, they had started with a 50 kilowatt, 500 volt motor with 6,000 RPM in a 10.6 inch diameter. In 2010, their optimized version was having the same diameter, higher power, higher voltage, and higher speed. And in 2017, they have gone with more optimized power, 600 volt voltage, and significantly higher speed, but much lesser diameter. So they have shrunk the size from 10.6 inch diameter to 8.46 inch diameter. So that is on the rotor. Similarly, on the stator, they have gone from 6.37 inch dia to 5.53 inch diameter, and also optimize the interior design significantly. The motor leads are also reduced in size. The total converter, the weight of the inverter, that has also significantly reduced from 16.2 liters or 13 kgs to 8.4 liters or 10.8 kgs. So significant reduction is there in the inverter weight as well. So these are the things how the optimization is getting happened. So when we are launching, Indian companies are launching the first products in 2019 or 2020, then we can estimate that by 2022 or 2023 they will reach some stage. 2025 they may reach a stage where the most optimized system is available. This is another example. This is coming from Nissan Leaf, between comparison between the 13 model year and the 2018 model year. And you can see that they have optimized, got to a higher power and higher torque at the same weight and volume, right? Higher current, higher power, higher torque. And from an inverter side, much lesser mass compared to the model year 13. So overall, they have optimized and saved. So rare earth elements, they have to have some level of additional coating, which is also expensive. And that expensive coating also becomes important to reduce in order to, or optimize in order to get the maximum element. So here there is a dysporium which is being used with the neodymium ferrous boron, but previously it was impregnated very inefficiently on the surface of the magnet. Then they have gone with only the grain boundary diffusion. So much better usage and much lesser quantity required. And then they have gone with grain boundary diffusion and grain refining. So even they have reduced the size of the grains and reduced the gaps between them. So over time, the reduction on the total use of dysporium has decreased by 70%. So that is also a cost efficiency element that they have achieved. So there are a lot of elements happening, lot of design changes happening in order to get the best. So by changing the teeth size and the back side, back yoke, we can pack more winding. We can give it better thermal characteristics, better thermal dissipation, and that is how we are seeing that optimization is getting done. So all these will be the lessons to be learned as we move along. So PM synchronous machines, they are meeting most of the requirements that we talked about initially. So higher power density, higher efficiency, easier cooling, higher reliability, better dynamic response, higher machine cost, and it goes higher machine cost because of the magnet. So that is the disappointment. There is some challenge with high speed operation if it is a surface mounted magnet. And then there is a chance of demagnetization or getting uncontrolled flux. So those things are going to be the uh, disadvantages of the machine. Then quickly we talk about the induction motor. And here the rotor is of a different variety or construction. So it feels like a lamination and a covering, but there is these cages. There is a cage and there is a covering on top of it. That is what we are seeing. Now these cage traditionally used to be copper cage, but in EV for light weighting, we are getting to see a lot of aluminum cages. Now within this, we can see how the optimization can be done in terms of how the current is going to flow with regards to the inducement of the current. So this is the flow of the induced current circuit. The rotor of Audi e-tron, we can see that here. So there is the squirrel cage. This is the aluminum squirrel cage. On top there is a laminated core. The cage rings are designed in a way that they also give some, they are like fan blades, so they also give some cooling. And then there is a hollow shaft which will also have a coolant flowing through the shaft. Right. So internally also we will be able to cool the rotor, which is very important because the heat generated in a induction motor is significantly higher. So induction motor technology, we have complete elimination of the rotor magnets. We reduce the rotor losses. Uh, if we go to copper cage instead of aluminum, but when we go to copper, there are other challenges. The drive cycle efficiency can be well designed, but it takes a lot of effort and calibration in order to make it work as good as the IPM machine. The magnetic field strength in the machine can be lowered via the stator current. So that is good. The flexibility is much higher in a induction motor. And the absence of magnets is reduces the potential for damage by short circuit. So rotor losses are generated. That is a problem. Heat losses in the rotor are significant. We have a small air gap requirement in order to minimize the reactive current and maximize the efficiency. Now, if we increase the number of poles on the stator, then it becomes very inconvenient to use a induction motor. So, for lower speed and direct drive applications, we don't use a induction motor. And when the constant power region we want higher, then we can optimize that. We can increase the constant power region and we can reduce the leakage reactance in order to get the optimized performance. Right, so quickly, synchronous reluctance motor. Here we see that the stator is the same, but with the rotor, what we have done, there are no magnets anymore, but there are cavities which then change the way the path is going to be there for the flux. So we can see the flux path here and very different. We are giving it a different reluctance path without having any magnets on the rotor. So we don't require field windings or permanent magnets in the rotor. So it is giving a higher mechanical integrity to the rotor. It is not expensive. It doesn't get demagnetized. It is not thermally unstable. But there is the operation is challenging in terms of meeting the high torque requirements. Right, so here we see two different type of rotor designs. So one is a 2 barrier, second is a 4 barrier. Right, so we have talked about the advantages of the synchronous reluctance motor. There is some elements that we have not talking in detail, which is the saliency ratios, which is basically talking about the flux flow path that will be developed in the synchronous reluctance motor. And what we have is today why they are not widely used, because they are not in demand, not being manufactured in high numbers. So the cost of the economies of scale do not exist for the synchronous reluctance motor. right? So here's an example of a synchronous reluctance motor which Tesla is using. So Tesla is basically using a IPM plus synchronous reluctance motor. And the way we can see the flux barriers are created. So it is having magnets, but at the same time it is having these cavities which are giving the variable reluctance path, right? So along the q axis the flux lines are obstructed because these flux barriers are there, and all the concentration of the flux is along the d axis. So the d axis the lines can flow through without any hurdles. Right. So I'll quickly shift gears. Give me 1 second. So most important is how do we select the motor? And for us to select, we have to understand the vehicle characteristics. What is the speed, torque, and power requirements? Then the drive cycle. What is the dynamic requirements of the motor? And whether we need a gear reduction or a gearbox or not. So that is there. Then what are the extreme characteristics? The maximum speed, maximum torque, maximum power, maximum weight. All of those are required to be known. Then we have to determine the voltage range. We have to be in agreement with the battery voltage. So firstly, the prime motive power, we don't want any step down or step up in this. So we want the motor and the battery to agree with each other. And installation space, mounting and integration, that is also very important to be known. So this is a typical torque speed curve of a motor. We can see that we hit very high efficiency zones like 94%, and we can lie between 80 to 94%. Now the question is, how much time are we able to spend in this sweet zone where the efficiency is always above 90? And that becomes the main calibration or main optimization on the vehicle. Now, when we look at this, we have to be mindful that we can actually get the peak torque immediately from a vehicle, from a motor. However, in order to uh, keep safety and not have a sudden inrush of current, it is tapered. So the torque we don't allow immediate rise because of the current increases significantly, right? So now when we are looking at comparing it to a IC engine vehicle, we have to look at the vehicle with a speed with a engine plus transmission. And the engine plus transmission, the entire curve of the first gear to the fourth gear, that should lie within the torque map of the motor. Only then we can properly use this motor uh, that is there, right, for a certain application. Now here again, so what we want is to stay in the maximum efficiency zone. How we can do that? That is the element that we have to use our control logics for. Now typically what we'll get. 1 second. 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 1 sec question then is, can we directly use that torque speed curve? Uh, but the torque speed curve given by the supplier, that is under some standard test conditions, which may or may not be similar to how we are going to use the motor. So the coolant flow rate may be different, the operating temperature may be different, inverter setting may be different, the control mechanism may be different. So we have to get to the right elements in order to be able to use the curve. Otherwise, we have to do our mapping and simulation and generate our own data. So if we look at the torque speed curve, then we have to distribute it in different segments. There is a peak torque that can be guaranteed. So our peak torque requirement from a vehicle perspective should never be greater than this peak torque. The speed till which the peak torque can be guaranteed. So we are looking at the speed at which the peak torque can be guaranteed. Uh, this is the speed. The base speed, then the RMS of the nominal torque. So there is a nominal torque. This is the peak curve. This is the nominal curve. So we should go across the nominal and peak only for a short duration and come back. We don't want to stay in this area for a long time between the peak and nominal. We go towards the peak and we come back quickly. That is how we have to use, select the motor for the application. And we have to obviously try to be in this sweet zone, like the RMS value zone. That is where the highest efficiency is going to be. And we don't want to go beyond a certain speed, or we don't want to go to a no stall torque. So there has to be protection on the high speed side. So we have to understand the curve coming from the supplier. The supplier would be making motors at different uh, uh, the voltage and different torques, giving different torques, and we have to understand what is better for our application. Now here we see the curves from a supplier, which is giving two different sizes of the motor, a 90 size and a 115 size. Now here we can see that with regards to the peak at 350, 500, 600 and 700 volt motors, as we go higher in the voltage, the amount of time, amount of speed till which the peak torque can be delivered is increasing, right? So that is the benefit that we are getting on the peak torque, and the droopage of the nominal torque is also getting extended as we move to higher voltage. Now, between these two curves, when we are going to a higher size of the motor, then we can see that the peak torque has increased. The peak torque has increased from around 325 to around 425 uh, Newton meter. So, as far as the curve of the droppage it remains the same. So it has actually reduced. So the drop will happen faster. However, now here the benefit is that the peak torque is higher. So the peak torque is available typically for 60 seconds. We have to refer to the spec sheet, but mostly it will not be for a value above 60 seconds. So that should be good enough for us to do an initial start of the motor. So once we have the base speed, then beyond the base speed, the peak torque is no longer available. It starts going off below a trend. And at some point, the power is going to become the rational line. So we have to see where do we go in terms of the extending the peak torque or the constant power. So that is the element that has to be looked at. This is also showing a relationship between the operating voltage and the power. So if we see as we go up in the voltage, the power is increasing, and if we then increase the size of the motor, that means the current is also increasing, then we don't see any impact on the voltage, but the speed at which the peak power is available is getting reduced. So I am going to enlarge my constant power zone by going to this motor. So constant power is enlarged. It is going to now start at a much lesser speed as compared to the curve above. We talked a bit about the back EMF. So each winding is generating a back EMF. This back EMF opposes the main voltage supplied to the winding, and the back EMF depends on the angular velocity of the rotor, the magnetic field generated by the rotor magnets, and the number of turns in the stator winding. So if we look at this, then most of the factors that it is dependent on is fixed in design. The only thing that is on the application changing is the angular velocity of the rotor. So that is going to be the change in terms of the on application impact to the back EMF. So as the speed increases, as the angular velocity increases, the back EMF also increase, and the motor will have a back EMF constant. So that constant, which is given by the supplier, that can help us estimate the back EMF for a given speed. Now, if the conditions exist where this back EMF is going to be greater than the EMF which is applied, that is when the regeneration is going to happen, right? So by design, there is always back EMF, which is already considered at the supply voltage. And even after considering the back EMF, the motor is able to draw the rated current and deliver the rated torque. So that is already taken into account, right? So always the motor is also behaving as a generator, but in the cases where the back EMF overcomes the battery, then the generator component becomes dominant, and we start seeing the regeneration. Now, regeneration obviously has to complete the full path to the battery. That means any other components like the motor controller or any DC-DC converter which is being used in the path, they have to allow a bidirectional flow or a opposite flow. So as soon as the motor overcomes the battery, the current starts flowing in the opposite direction and feeding into the battery. So this develops a counter torque that acts as a brake, and this is called as regeneration. So now we have seen that nearly every motor is able to give a 90% plus efficiency. Now, if we want to differentiate, if everyone is using a random motor, every EV is able to get a greater than 90% efficiency. So how does a OEM or a manufacturer differentiate? How can they do better than the others? And the biggest differentiator that is going to come in the EV is cooling, or let us say overall thermal management. Whoever does the thermal management better is going to have success in this market. Now, the thermal management can be done in different ways. We can add air-based cooling, we can add water-based or coolant-based cooling, we can add air conditioner. There is a lot of methods in which we have to look at this. So let us see what the biggest members are doing. Right. So here, the Audi e-tron type of platform, we can see how they are doing the cooling. They are cooling the power electronics and then cooling the stator and rotor as well. Right. So rotor is getting internally cooled and all of that is going out. Right. So that is how the complexity of the coolant architectures, the end plates and the bearings are also getting cooled. So overall, that is what we are seeing as the complexity. So this is as complex as cooling the engine, just that here, unlike the engine, there is no requirement to go to a oil-based cooling. There is no metal-to-metal connection that we need to lubricate within the motor. Now, the effect of the rotor internal cooling system can be seen. We can look at how the temperatures are very different when the cooling is employed and how hot it gets when the cooling is not there, right? So this can cause a lot of damage if we are consistently having high temperature excursions. Right now, so this the cooling architecture becomes the most challenging element that has to be looked at, and we have to look at how optimized cooling can be given. Now here, what we are looking at is the torque and the current which is being delivered to the three phases. We have phase A, B, and C. This is a typical BLDC motor with distributed or with the windings. Now, the A, B, and C are not drawing the current at the same time, and all this turning on and turning off, this electrical commutation, this has to be achieved by a circuit, by an electronic circuit, and that is what the motor controller is doing. And this portion of the motor controller, which is activating the switches on and off, is called as the inverter. So need of a motor controller, first of all, we need to control the dynamics of the motor, that is the speed and the torque. We need to provide the electronic commutation and the sequencing as we talked about. We need to ensure that the motor will start by itself. We want to protect from damage and abuse, and we need to match with the supply source. And in some cases amplify the input voltage. So all of these are requirements which are calling for the need of a motor controller. The motor controller is going to take a speed command. This can be via a potentiometer, or it can be coming via some other controller or a master controller, which is going to give it a speed command. And it is taking the voltage input from the battery, having these multiple switches, two switches for each of the winding, one to take the winding to positive and one to take the winding to negative. And with that, it is turning on and off the different switches. There is a forward reverse switch, and then we have some sensors on the rotor or on the end plate, which are giving the sensor feedback to the controller. These are Hall effect sensors, and they are spaced in a way that we can judge the location of the stator winding relative to the magnets. They will give a 0 and 1 signal, based on which we decide which taps or which gates to turn on and turn off in the next cycle. Right, so here we are seeing a simplified diagram. So as we get the different Hall sensor inputs, we are able to take that and look at which phase needs to be energized for getting the next sequence. And this sequence is provided by the motor manufacturer. So the motor and the motor controller have to sync up on this sequence. The proper windings need to be connected to the proper outputs of the motor controller in order to make this work. Right, so here we are seeing the state of Hall sensors 101, wherein the phase A is positively energized and phase B is going to the negative terminal. Then we move to A and C, wherein the phase A remains positive, and now instead of phase B, the phase C is connected to the negative terminal. The phase B is not connected. So all this needs to happen in a very synchronous manner. Right, so there is a overall commutation table which needs to be followed, and that is what is going to be there. Right, so there are different control techniques. As we talked about, the simplest way is to do a simple control of the BLDC, speed-based control, wherein we have the trapezoidal control if it's a BLDC, and a sine wave control if it's a AC motor. We can go to more complex algorithms like field-oriented control, wherein we can use different type of sensors, or we can also have it sensorless. And then we have the induction motor, which typically traditionally uses voltage by frequency control, or VFC, which can be sensorless. And we have the direct torque control, which can be sensorless or sensored. So direct torque control is very similar to the field oriented control on the DC side, or BLDC side. So most controllers are going to be running two control loops. One is the inner control loop, which is looking at the currents for the optimal torque generation. And the second is the outer control loop, controlling the torque reference and the field weakening logic. So the master controller, or let's say the throttle or the accelerator pedal, whichever depending on two-wheeler versus four-wheeler, and the brake. All these inputs come in, and based on that, a required torque is generated. This required torque is then used to generate the amount or to compute the amount of current that will be required in order to generate this torque. And that once that is known, then the current is given to the winding. And we expect now that the actual torque which is obtained is there, and we need to compare the two torques to see whether we are deviated or we are meeting the expectation. So the vector control, also called as field oriented control, uh, in this case what we do, just like the D field, D flux and the Q flux, here we are doing the separation of the current into two orthogonal components. So we are distributing it into two orthogonal components, which can be visualized as a vector. One component defines the magnetic flux of the motor, and the other component defines the torque. So one component is more linked to the flux, the other component is linked to the torque. And we are going to control both of these components directly so that we can get to the torque value that we desire, but also go to the most optimized flux value for that particular torque, right? So this gives us the ability to have a optimized and a efficient operation over the entire speed range, generate the full torque at zero speed, and have high dynamic performance. So that is something which is achieved by the field oriented control. So here's an example of the total control methodology. We have, as I said, the brake pedal, accelerator, vehicle speed, and the battery voltage. Based on all of this, we are creating a demand torque or required torque. This demand torque is converted into the quadrature components. How much I want in Q field and how much I want in D field, right? So these two currents are generated, based on which we are looking at what are the current values of those currents. What is the actual value right now? And we are comparing the two, summation block, and whatever is the error, only that is going into the control loop. So we are taking the error, and then we are computing what is the required field currents. Now for this, we want to ensure that we are getting the actual current, and for that we may need a inverse transformation, or we may need to convert it into AC waveform. So from a DC we go to AC, right? So this may be a trapezoidal control or it may be a sinusoidal control. So we are going to match it to the control methodology and then convert it from a two orthogonal components. I don't have direct application of these two currents on the motor. What I have on the motor is phase A, phase B, and phase C. So I need to know what current needs to be applied to phase A, what needs to be applied to phase B, what needs to be applied to phase C. So that is what is computed here. Accordingly, then how much PWM or how much time the gate has to be opened, that is looked at, and 6 signals for the gate are generated and fed to the inverter. The inverter is the only thing here working on high voltage. Rest all is working on low voltage. So here the inverter on the other side is connected to the battery, and based on which switches are open, it is going to apply the currents to the three phases. These currents are getting sensed by means of a Hall effect sensor, or maybe some even absolute measurement, and then again converted to the two orthogonal components and taken into the error statement.
Shekhar sir?
Yes,
Sir, actually we are running out of time.
yeah,
It's already been 15 minutes late, sir. So can you just conclude the session, sir?
right. Somehow I felt it was slightly longer session.
Yes, sir.
Overall, there are a lot of elements in the inverter design as well, which needs to be optimized, and a complete selection of the motor and motor controller has to be done in order to meet the requirements of the application. So that's all from my side. Any questions? We can take them.
Yes, sir. There are a few questions. I will just convey it. Like one question is, which is preferably the best BLDC hub motor to be used on electric bike in terms of power and range?
So which, as in, are we talking about a manufacturer? So radial flux machines are there, and now axial flux hub motors are also coming out, which are bound to be slightly more efficient than the radial versions. So that is something that you can look out for. There are a lot of manufacturers who are in the final stages of R&D in that terms.
Okay, sir. The other one is, do we have any platform to purchase cost-effective motors for simple e-vehicle designs?
There is no platform as such where a direct quote from the supplier can be taken, especially now that the China supply chain is totally hampered. But there are platforms like one that we also have called Gyaniki. Uh, at Gyaniki, you can at least get in touch with or get to know who are the suppliers, what are the motors they are making, and what are the specifications of the motor.
Okay, sir. So can we use sensor to run BLDC motors?
Yes.
Okay, sir. Is there any flaws on BLDC hub motor when we use it on ADV electric bike?
Or use it on
ADV electric bike.
ABB electric drive or ABB
Bike.
electric bike.
Bike.
Okay.
Is the
I
question, sir?
don't. Yeah, I don't see any problem there.
Okay.
If we are using the right motor controller, then the motor should work.
Okay, sir. Those were the few questions, sir. And sorry to limit your session, sir, because we are running out of time already. We are 15 minutes late. In that perspective, I have just interrupted you. I'm really sorry for that.
No problem. No
So, with your permission, can I just conclude the session, sir?
problem. Yes, please.
Okay, sir. So, thank you, sir. Thank you for the wonderful session. It was very, very informative for us. And so, we would like to thank on behalf of all the participants and the organizers, Bangalore Institute of Technology and Engineering, sir. Thank you for the session, sir. And dear participants, the next session will be on thermal management in EV by Mr. Ravi Ranjan from Mahindra Research Valley, and it will start exactly at 2 o'clock. So we shall break for the lunch and join back at 2 o'clock. Thank you, Shekhar, sir, for your session.
Yeah.